Good morning, everyone. We're going to continue this morning in Chapter 4. We're in the early part of Chapter 4. We'll be discussing Chapter 4, probably new content through Wednesday next week, and then hopefully into some review topics on Friday, and then into the following week into Midterm 2. This slide here, we were discussing this a little bit on Wednesday, but this slide here is showing us mixing two clear reactants, two solutions that don't appear to have any solids in them. And so we have Ki in one of the beakers, and then in the other beaker we have lead nitrate. Now, lead nitrate contains nitrate. All nitrates are water soluble, so that's a water soluble compound. So in other words, it's completely ionized into lead ions and nitrate ions, all surrounded by individual little water spheres. We're not showing all the water spheres of the water molecules in these little graphics. And then we have our ions, I minus and K plus for our Ki solution. So we're taking Ki, potassium iodide plus lead nitrate, mixing them together. And what we're observing is that when we sort of swap the ions, the two, like imagine swapping the lead and the potassium and making lead iodide and potassium nitrate. Potassium nitrate is perfectly water soluble, contains potassium. Anything with potassium is water soluble. Anything with nitrate is water soluble. And then, but the product lead iodide, PbI2, lead 2 plus, so it takes two I minuses to balance out the formula, but that's an insoluble precipitate. That's from our solubility chart. That's one of the exceptions for the usually soluble iodide ion that's soluble with most other cations, but with the exception of silver plus, lead 2 plus, and that goofy Hg2 2 plus cation. And so because lead iodide is a solid, it precipitates out of the solution, and that's what we see here forming is that lead iodide. And generally solids are more dense than water, so they usually sink to the bottom of your beaker here. And so we're just seeing that we're forming a precipitate, so we call this a precipitation reactions, and that's when we mix solutions that generally contain soluble salts. Salts are another word for ionic compound. So we're mixing these salts or ionic compounds and then leading to an insoluble compound to form. And it's actually a hard requirement that one of the products be a solid, otherwise we wouldn't really observe a change taking place. So we have to have one of the two products of the reaction be insoluble in water to actually have this reaction take place. Otherwise, it would be no reaction. The next slide is going to try to get into why that's the case. We have a couple other words for this reaction. We call it a precipitation reaction. We also call this a metathesis reaction. So you'll see that used a fair bit. So a metathesis reaction is just a precipitation reaction, a synonym for it. Sometimes you'll see the word double displacement used. I don't use that so often. I don't think you'll really see it, but you may have heard this called a double displacement reaction. Now, how do we know to predict when a product is going to form that's insoluble, or how do we predict the products in the first place? Well, let's take a look at an example. We're taking cobalt 2 chloride. So cobalt 2 is cobalt 2 plus, chloride Cl minus, so CoCl2. Sodium sulfate, sulfate's a 2 minus, so it takes two sodium pluses to balance out the charge. So Na2SO4, so we're taking solutions of cobalt chloride, sodium sulfate, mixing them together. Now these are both AQs because they're water soluble. The cobalt chloride's water soluble because it's not one of the exceptions for chloride ion, and then the sulfate contains the sodium ion, which anything with sodium is water soluble. And so then what we want to consider is just either swapping the cations with each other or swapping the anions. We're just trying to see then if we exchange the ions with each other and then make cobalt sulfate and sodium chloride, or either of those products insoluble in water. So we can start thinking of our tags here. Water soluble is AQ. And then if any of those products are insoluble in water, we would write solid. But when I think of the solubility chart for sulfate, I could inspect it. If you need to double check, that's fine, but cobalt 2 plus is not one of the insoluble exceptions. So that would be an aqueous compound, so water soluble. And then NaCl is also an AQ, water soluble, contains sodium. Sodium's not one of the exceptions for chloride either. So we can inspect that table. You'll get that table on exams, the solubility chart, to use it to be able to predict if either of those two compounds are solids. So when everything's an AQ, this turns out to be a no reaction. So no reaction actually takes place when we only have aqueous or water-soluble ions forming as our products, because we started with a solution of ions that mix together. we end with the solution of ions that are just all mixed together. So there's no actual chemical change because we didn't form a solid. So no solid equals no reaction. So there's no actual chemical change taking place. So no solid, no reaction. The next slide will kind of show us a little bit more schematically why that's the case. So let's take a little bit of a closer look here at this reaction. So again, same reaction from the previous page. Now we call this reaction here, written out in this form here, we call it a full molecular reaction. Even though there's no reaction taking place, we would call the sort of idea of writing cobalt Cl2 AQ, we call that quote unquote molecular. It's not molecular, it's an ionic compound. So that's why I have molecular in quotes, but we're writing it almost as if it were molecular and sort of linked together. We know cobalt chloride, because it's water soluble, because it's an ionic compound, is really its ions in solution. It's really ionized as cobalt 2+ and 2 chloride ions. So we ionize all the strong electrolytes. So we just want to make ions out of all the things that are strong electrolytes, which all of these compounds are ionic compounds. They're all water soluble. So if it's a water soluble ionic compound, then it has to be fully dissociated into its ions in solution. So the sodium sulfate would be 2 Na+, 2 sodium ions, and then a sulfate ion. And so then the AQ tag, again, just for water soluble, each of those ions individually surrounded by its own little water sphere. Okay, so I have a collection of, and really the reactant should always be a collection of cations and anions. And then the question is, do any of them pair up and form that solid that leaves the solution? And so then when I think of cobalt sulfate, AQ, ionic compound, water soluble, so it's also ionized as cobalt and sulfate ion. Sodium chloride, of course, is a water soluble ionic compound as well. So it's ionized into Na+ and Cl-. And so if we just take into account the stoichiometry, the balancing of the reaction, we then see that we have 2 sodium ions on both sides, we have 2 chloride ions on both sides, we have a cobalt on both sides, and we have a sulfate on both sides. There's no net change. There's nothing that's actually changed within this mixture that we would have mixed together here. So we could start with the solution of cobalt chloride in one beaker, a solution of sodium sulfate in another beaker, mix them together, maybe think that there's a reaction taking place because I wrote that full molecular reaction, but as soon as I put AQ tags on everything, I know I'm just going to have a collection of cations and anions that are all just mixed together where there's no actual chemical change taking place. So there's no net change, so there's hence no chemical reaction taking place. All the ions are what we call spectator ions. A spectator ion is an unchanged ion during the course of a reaction like this. So an ion that doesn't change form is a spectator ion. So all the ions are just spectators. They're all just watching the water. They're not really doing anything. There's no net change taking place. So the next step would be to obviously compare this to the case like the lead iodide forming or some other reaction where there is a solid forming, just to see the difference. So let's take a slightly different reaction. Here we take the same cobalt 2 chloride, but we switch to sodium carbonate. So instead of sodium chloride, we use sodium carbonate. Sodium carbonate would be Na2CO3. And then we then think, okay, I take my one reactant here, cobalt chloride, that's of course water soluble still. Sodium carbonate is an AQ, water soluble. So I'm just thinking here, by my solubility chart or my understanding of solubility, is the compound insoluble S or AQ soluble? Now, when the question is telling us aqueous solutions of those compounds, you kind of know by the nature of the question that they have to be AQ. Like we're almost telling you there's solutions of those things, so they have to be water soluble, otherwise this question doesn't make any sense. Okay, so we have water soluble salts to start, and so then cobalt carbonate, is that water soluble or insoluble according to our solubility chart? That's an insoluble salt, so that should be the solid that's going to drive this reaction to take place. That's going to allow a chemical reaction to occur within the mixing of these two solutions. Why is it a solid? This has to do with the solubility chart. So we inspect that solubility chart. Carbonates are generally insoluble. The exceptions that are soluble for carbonates are ammonium cation, the alkali cations, and calcium, strontium, barium. Cobalt, of course, isn't one of those, so it's just a regular insoluble compound in water. And then sodium chloride, of course, is an AQ. And it's usual that just one of the two products is a solid. It's kind of not the case usually that you need or see both of them being solid. So usually you get an AQ and a solid when there's an actual reaction taking place. So does a reaction take place when these two solutions mix? Yes, it's going to be the formation of that cobalt carbonate that drives a reaction to taking place. So let's do the same thing with this reaction. Let's try to break it down like we previously did for the reaction with sodium sulfate. So we take our cobalt chloride, separate, write it as cobalt 2 plus AQ plus 2 chloride AQ. Sodium carbonate, water soluble. So we write 2 sodium plus the carbonate ion. So we're just dissociating the water soluble ionic compounds that are strong electrolytes. So remember, a strong electrolyte is just a compound that fully dissociates. Any ionic compound that is water soluble has to fully dissociate. That's the whole process of it mixing in water, is the water molecule surrounding the cations and anions separately, breaking apart that salt. Remember, plus minus charges are strong attractive forces. We're replacing those with their attractive forces with water, but not every ionic compound can do that. So cobalt carbonate, when the cobalt and the carbonate ions bump into each other, they stick together. They then form a lattice structure, solid, where we precipitate out that compound. So we form cobalt COCO3 solid, and we don't separate that into its ions because it's a solid. Those ions are not in the solution. So think ions in solution, AQ, ions that are stuck together with each other in solid form. We just write the compound's formula with a solid. And then NaCl, of course, is 2Na plus and 2Cl minus dissociated into its ions. And so then you can kind of see here, hopefully, that the spectator ions are the sodium and the chlorides that are unchanged in the reaction. Now, they don't disappear. They don't annihilate each other. They don't disappear. We can just cancel them out from the net change. So when you write the net reaction, we call it the net ionic reaction because they're ions and the net change. They're the net changing ions during the course of the reaction is cobalt AQ, cobalt 2 plus AQ, carbonate ion AQ, precipitating as cobalt carbonate solid. So this is our net change. And when you can write a net change, you know a reaction takes place. So if we were to say, does a reaction occur when you mix cobalt 2 chloride with sodium carbonate? The answer is yes. We do get a reaction to take place. It is the formation of cobalt carbonate. What are the spectator ions? They're the unchanged ones. It's the sodium and the chloride. So the key is we can't just have all the ions be spectators in order for there to be a chemical reaction. For there to be a chemical reaction, we have to form a solid precipitate. So those ions are leaving the solution, causing a change to take place. Okay, so we'll have a few examples of like writing reactions too. We'll see acid-base reactions are kind of similar to this. Probably today in lecture towards the end, we'll be writing some acid-base reactions that kind of have a similar process of like a full quote-unquote molecular reaction. Now we call this the full molecular reaction like this because it looks like those compounds are being written as if they were molecular compounds associated together when we really know that they're not. We do this a lot. So we'll write NaClAQ even though we know it's really Na plus AQ, Cl minus AQ. So it's just kind of, we will write things like they're associated because it's useful. It helps us write reactions a little bit neater. If we want to get to the net change, we have to ionize the strong electrolytes, cancel out the spectator ions, and then identify that net change. Now let's take a look at a question like this where it's asking us which solution when mixed with barium nitrate's of course water soluble. So what solution when we add it to a solution of barium nitrate leads to the formation of a precipitate? Try this question, spend a minute or two on it. You can compare with your neighbors. You can use the solubility chart from earlier in the notes too. So give this one a try. Okay, so I don't know if you need to write all these reactions out. You probably don't need to, but I figured I would take the time as you guys were thinking through the problem. Now, did anybody think the answer was A? Anybody think it was B? B is kind of a trick because a lot of lead compounds are insoluble in water, but lead nitrate's not water insoluble. So if I mix the nitrate and the acetate ions with each other and think, is lead nitrate water soluble or insoluble? It's still water soluble. Barium acetate, the C2H3O2, is just the formula of acetate. All acetates are water soluble, so we don't get any solids forming for the first two compounds. So it's not A or B. Now C looks kind of close because a lot of hydroxides are insoluble, but not calcium or not barium hydroxide. So if I switch to barium hydroxide, that's still water soluble according to our solubility chart. So barium hydroxide is an AQ because according to our solubility chart, it's water soluble. So it's one of the soluble exceptions for the usually insoluble hydroxide ion. KNO3, of course, is water soluble. Then I get to the barium switching with the potassium to make BaSO4. Barium sulfate, now that's an exception that's insoluble. So sulfates are generally soluble with 4 listed exceptions on our chart, and it's lead ion, that goofy Hg2, 2+ ion, and then barium and strontium. And so we see here that this would be a solid, and so that's the one that precipitates. So we get a precipitate to form when we add the K2SO4 because we're going to precipitate out barium sulfate in part D. So I don't know how obvious this is. I don't know if, like I said, I don't think you necessarily have to write out all these reactions, but writing out the reactions lets us see that in A through C, all of the products are AQs, water soluble, so no reaction taking place. Only in D do I get a solid to form. And I'm just applying my solubility rules after switching the ions around with each other. Okay, now let's get into a discussion of like acids and bases. Let's start with acids. And there's a few things that we'll just take for granted here. Like if you remember the demo we did, we saw a solution of HCl on Wednesday and it lit up the light bulb. A solution of acetic acid did not light up the light bulb fully. It lit it up a little bit. So we were getting some ions with acetic acid. Acetic acid was the acid that was partially lighting up the light bulb. And then HCl was strongly lighting up the light bulb. So if you do that experiment and with 7 different acids, you'll see that they strongly light up that light bulb and are strong electrolytes in water, meaning they fully dissociate into H+ and then their counter ion. So those 7 strong acids, and we're just gonna have to commit these to memory. It's the only way to really know which of the 7 acids are strong, but it's HCl, HBr, HI, nitric acid, chloric acid, HClO3, perchloric acid, HClO4, and then the first hydrogen off of H2SO4. Okay, so let's digest this for a second. So what this means, if we take any of the, let's say the first 6 that only have 1 hydrogen. So let's take HClO4. HClO4, if I think of this compound in water, let's think of it as a water-soluble compound as an AQ, it turns out that it fully dissociates into the counter ions of H+ and perchlorate ion. And then this reaction here takes place to 100% yield. Now I write the 100% for the thought that it completely takes place. It's not one of those equilibrium reactions. Now let me contrast this with something like HF or what we saw for acetic acid. I'll write HF here because it's also useful to note that hydrofluoric acid is unlike the other 3 members in its group of the halogens, where HCl, HBr, HI are strong. HF does this partial. Now, how I indicate a partial reaction is usually with the equilibrium arrow to indicate that the forward and the backwards reactions are always taking place. So sometimes an HF will dissociate, and every now and then they bump into each other and reform. And there's what we call a dynamic equilibrium that gets established within a solution of HF and water. And that equilibrium discussion is for later. So you'll talk about the equilibrium events, equilibrium constants in Chem 1220. But for HF, what I like to think is that the yield of the reaction is less than 100%. So it's like 5-10% yield. So you get some H+, just not a lot of it. So if you think of having ions in solution as being what conducts electricity and allows the solution to be electrolytic, the HF solution has a few ions within it, just not very many. So if we compare that to HClO4, a lot more ions. If you compare that to HCl, same number, but H+ and Cl- ion. So the first 6 of the 7 strong acids lose their 1H plus fully. H2SO4 is a little bit weird where it has 2 H ions, but only the first one falls off to 100% yield. So if you imagine having a soluble H2SO4 molecule, it 100% dissociates to H plus, and then that HSO4 minus ion, if you remember, that was hydrogen sulfate ion. And then the hydrogen sulfate ion, let me write this over here, that this ion losing that second H plus to go to SO4 2 minus, that becomes a less than 100% yield. And then we indicate that with the equilibrium arrow, or just the idea that it doesn't fully fall off of the HSO4 minus ion. So it's a little bit complicated, but it's like if you have a solution that we call HClAQ, it's really like NaCl. It's really H plus and Cl minus. If you have a solution that we call H2SO4AQ, it's really a lot of things. It's really H plus, it's really HSO4 minus, it's a little bit of SO4 2 minus. It's just not 100% SO4 2 minus. We still end up with a fair bit of HSO4 minus. The equilibrium stuff is really the gory details. You see that later. So at least we don't have to go through and calculate and quantify with like equilibrium constants just yet. So we're just trying to introduce the idea of what it means to be strong, fully dissociated. So we're making ions, so we still call these electrolytes. So if you notice, our strong acids are still strong electrolytes because they're ionizing, but specifically to H plus. So the thing that we call an acid is where the cation is specifically H plus. There's other definitions of what it means to be an acid or base. This is just like, we don't even use this term in chapter 4, but it's the Arrhenius definition of acids and bases if you're familiar. There's other definitions of acids and bases if you recall, if you've seen them before. But this is just a simple definition that what makes something be an acid is forming H plus in water, and what makes something be a base is either consuming H plus or being linked to H plus in water, the OH minus ion. So we'll see in a minute that bases are things that make the counterpart to water, the OH minus ion. Okay, so now our weak acids include all the other acids from our nomenclature, which is kind of nice in a way. It's very circular. So it's circular in the thought that we learned how to name a bunch of things as acids. The 7 of those things that are above, we have to memorize as being strong acids. So notice that they're all ic acids. So it's hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, perchloric acid, and then hydrochloric acid. It's not all the ic acids, like phosphoric acid's not on the list. That's a weak acid. H3PO4 is not a strong acid. Acetic acid is also a weak acid. So being an ic acid doesn't make an acid strong. But if you notice, there's no OUS acids. There's no US acids that are strong. So sulfurous acid, nitrous acid are all on that weak acid side. We even include HSO4 minus here as one of those weak acids. And then all the other acids we learned how to name, which weren't that many. But if you know how to name something as an acid and it's not one of the 7 strong, the implication is that it's a weak acid. Lastly, these are inorganic acids. We haven't learned anything about organic acids. When you get to OChem, you'll learn that there's organic strong acids. So we're kind of separating for the inorganics here. These are the inorganic strong acids. There are such things as organic strong acids. You can learn about those later if you take OChem. Okay, and there's other things that look like they might be acids, and once we see bases, maybe you might think they're bases, but we have to be a little bit circular in things that the things that we're naming as acids are kind of inclusive of all the things that we've seen or will see that are acidic. You know, so when you see a formula like methane, that you might think, oh, is that an acid and we just didn't tell you or didn't name it as such? No, CH4 is not an acid. It turns out not to be a base either. Water is actually not very acidic either, so water is neither an acid or a base. You can get it to act as a water or a base. You can get it to like lose an H plus or form OH minus ions, but it's not going to do that just on its own very plentifully. Methanol looks like acetic acid, right? Because I think we mentioned this before. Like the alcohols look similar to the carboxylic acid group, but to be an acid on the organic side, you really need that COOH group. So that's the one organic acid functional group that we learned was that COOH group, that this is the acidic group, and then the alcohol group is not acidic. So ethanol is not acidic. Glucose, sucrose aren't acidic. They're not bases. So we're going to be circular in our reasoning that if something's not an acid, we'll see bases in a minute, but the bases are really going to be limited to compounds we've already seen before, like ammonia or some water-soluble hydroxide salt. So you'll really be able to notice bases too. So these compounds aren't bases either is what I'm trying to say here. Okay, so we're memorizing the 7 strong acids, and then kind of all the other acids we know how to name are weak acids. We can also classify acids as being monoprotic or diprotic or triprotic or higher protic per how many H plus ions can dissociate off the compound in water. Now, it can still be weak, and we would still call it a monoprotic acid. So for example, HF, we would say is a monoprotic because it has 1 H plus, and we'd call it a monoprotic weak acid. HCl would be a monoprotic strong acid. HNO2 would be a monoprotic weak acid. So to be a monoprotic acid doesn't imply that the acid is strong. It can still be weak or strong. It just means it has 1 H plus to lose into the solution. So a diprotic acid, again, whether it's a strong acid or a weak acid, we can classify based on how many H plus ions there are available to dissociate. We could classify H2CO3, carbonic acid, as a diprotic weak acid because it's not one of the 7 strong. And then H2SO4 is a diprotic strong acid, but again, only for that first hydrogen. So diprotic acids because they have 2 H pluses that they can lose. So a good example of a triprotic acid is H3PO4 because 3 H pluses that it can lose into solution. It doesn't do it just in water, but we'll see if you add something like a base to it, you can kind of kick those H pluses off. So we'll see that in a moment. But we would call H3PO4 a triprotic acid. Now, if we then look at something a little bit more complicated like citric acid has these carboxylic acid groups. It has these CH groups. It has an alcohol group. And so you may be looking at all these hydrogens and saying, well, which of the 3 are acidic? Or which of them are acidic? Well, it's only the 3 hydrogens that are part of that acidic group. So the other hydrogens are not going to fall off in water. They're not going to fall off if we add base to the solution. They're going to stay intact. So these bonds here are not breaking under ordinary conditions. So those stay intact. Only these 3 here are the acids, the H plus ions that can fall off into solution. So citric acid is triprotic, and it's these 3 here. And the other ones stay intact. Like if we go to acetic acid is another good example. If we look at acetic acid, do you want to call that monoprotic, diprotic, triprotic, quadriprotic, or whatever that would be, tetraprotic or whatever? Do we think it has 4 H pluses that can fall off into solution or just 1? Just the 1. And so the thought, it's very circular, but the thought is, I would be thinking, do I know how to name the things if those other H pluses fell off? And I don't, so we have to be sort of circular in the logics that the way we introduce acids is they're H plus ions with some underlying anion that we know how to name. So if we lose the H plus, we can name the anion that's left behind. And you could sort of start to think, well, if I lose the H plus, do I recognize something I've seen before? If I lose one of these H pluses, do I recognize what's left behind? I don't. That's not something that's going to take place. Those CH bonds are too strong, so they're non-acidic. So this is monoprotic. So let's look at bases and define what it means to be a base. The simplest definition we're using in this chapter is that it's a compound that releases hydroxide ion into water. So it's a water-soluble compound that can release that hydroxide ion into solution. And so there are strong bases, strong electrolytes, and water are examples that do this. So if you look at this, the category of compounds that contain hydroxide ion, that are ionic compounds that contain hydroxide, we have all of those exceptions for hydroxide. So ammonium hydroxide, we have the alkali hydroxide, so we have lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. We could write francium, but it's radioactive. We're not going to see examples with francium. And then we also have calcium hydroxide, barium hydroxide, and strontium hydroxide is in the wrong order. Strontium is wedged between calcium and barium on the periodic table, but then strontium hydroxide. So all of those compounds there, when they dissolve in water, all those compounds do dissolve in water. They're all the water-soluble hydroxide exceptions, and then they're going to dissociate into cations and anions. So let me do this with strontium hydroxide. So if I have strontium OH2 in water, so if I imagine putting the solid compound into water, so I add it to water liquid, then I'm going to form strontium 2+, and I'm going to make the 2 hydroxide ions to 100% yield, because this is a water-soluble ionic compound. Probably this slide should say bases, since we're talking strong bases first. Like this slide's talking strong and weak bases, so the title did not make sense. So I might cross weak out on your slide. So the strong bases are the compounds that we already know to be soluble, that contain hydroxide ion, that release hydroxide ion into water. There's some complicated compounds that we don't talk about that we could talk about, like oxide ion. Sodium oxide is water soluble, like Na2O. And we know it's soluble because anything with sodium is soluble. Now, oxide ion, O2- is going to react with water very readily. This compound actually can burn if you add too much of it to water. It actually can ignite because it's so, the reaction is so exothermic when it reacts with water. It's going to take an H+ off water, make an OH- ion. My point here is other things can do things like hydroxide salts and lead to the formation of hydroxide ion through other reactions. You may have seen oxides before listed as being strong bases in water. We're not really discussing those in this chapter, though. So we're not getting too deep into a discussion of other things that can also make hydroxide ion in water readily. Hydride ion does this too. Hydrides are very reactive, so they're very dangerous to work with. An H- ion would react with water to make OH-, and the other counterpart would be OH-, but we're not going to get into that discussion, into that level of depth. You may have seen some of that before. That's why I mentioned it here. And then also, our weak base discussion is going to be really, really basic, or really, really simple, because we haven't really seen a lot of complexity of molecules to really recognize things that might look like or be similar to the one molecule we're going to show you, which is ammonia. So our main prototype of a weak base, which ends up being a weak electrolyte in water, we saw it with that opening demo we did on Wednesday, was NH3AQ, where it was reacting with water, or we were seeing that it must be reactive with water because we were seeing some ionization, just not total ionization, where it was making NH4+, and then some hydroxide ion, where these are water soluble. And so we just get less than 100% yield of our ammonium and hydroxide cation and anion. So we're getting some reaction, some formation of hydroxide. And so that's why we look at ammonia and say that it makes some hydroxide, just not like 100%. So if this reaction were to go to 100% yield, then we would have said ammonia is a strong base. But because it goes to less than 100% yield, the yield on most of these partial reactions is like less than 10%. So you don't get that much. So we call ammonia to be a weak base and then a weak electrolyte. So we're getting some ions, just not that many. So we didn't light up the light bulb very brightly. It was a dim light bulb, so a weak electrolyte. And because one of them is hydroxide ion, we call ammonia a weak base. Now, there are things that look like NH3. Like if I write NR3, if you've seen OChem, you might know what the R means. It could be a methyl group, an ethyl group, a phenyl group. If you haven't seen any OChem, it doesn't mean anything to you. So I might be able to have you recognize that like NCH3, like ammonia has a lone pair of electrons, and even that's something we can't predict or see because we haven't really talked about Lewis structures yet. But when we get the Lewis structures, we'll see ammonia has a lone pair of electrons on nitrogen. If you have nitrogen with a lone pair of electrons, usually it will act like a base. NCH3 does, or NCH3, that's trimethylamine. But we don't get too tricky with the weak bases. We usually just limit it to NH3. So you can recognize and see, and there are other things that are weak bases, they're not that hard to picture, but the problem is, like, you don't know how to structurally look at these things to see if they have a lone pair of electrons on the nitrogen atom. So we usually just limit the discussion to ammonia. We usually limit the discussion of strong bases to just the hydroxide-containing water-soluble salts that we learned from the early part of this chapter. Okay, a couple of flow charts. This one is the flow chart currently in the book, and I'll show you in the next slide one from actually my textbook edition that I used from the same textbook authors from when I was an undergrad. But this chart here is very complicated because it's showing us the electrolyte type for water-soluble compounds. And it does kind of lead us to a small discussion that we've only predicted water solubility for ionic compounds. So in terms of compounds that are soluble, we've only gone through trends and predictions for ionic. Like, we haven't really talked too much about what it means to be a molecular compound that's water soluble. So if we show you a molecular compound, like if I say propane, is propane water soluble? We haven't talked about that. It probably isn't, but you probably don't know that. And we don't have a good mechanism for how to predict if a compound is soluble or not if it's molecular. But if the compound is molecular and it is soluble, we can then at least classify what type of electrolyte the compound would have. Okay, so let's look at ionic first. If you know a compound's ionic, from our solubility chart, we can predict those that are water soluble. All of those water soluble ionic compounds are strong electrolytes. You know, that is the mechanism by which an ionic compound dissolves into water. So there's no examples of weak electrolytes or non-electrolytes that are ionic, that are also water soluble. So for ionic, picture it like this. If it's something like PbI2, PbI2 is a solid, it's not in water, it's not an electrolyte. Do you notice how, like, this is so confusing. It's like non-electrolyte is different from not an electrolyte. A non-electrolyte is something in the solution that's not ionized. Something that's not in the solution can't be classified as any kind of electrolyte. So this is kind of like a not applicable in Na, or it's not any kind of electrolyte when it's insoluble. It's not being considered in the above chart. So something like PbI2, if you say, well, classify PbI2 in the above chart, it's not in the chart because it's not a water-soluble compound because it's water insoluble. So water insoluble, that's a bad, this is just insoluble. So it's not included in the water-soluble chart. Now, if we had something like, for some reason, there's certain like compounds like MgOH2 that get a lot of people off guard. A lot of people call this a weak electrolyte for some reason. I'm not quite sure why. MgOH2 is just insoluble as well. So it's also not applicable to call it any type of an electrolyte. It's just not in the solution at all, so we don't classify it as any type of electrolyte. If we then look at anything like KNO3, KCl, anything water soluble has to be a strong electrolyte. So if the compound's ionic and it's water soluble, has to be a strong electrolyte in water. It has to be fully ionized. Now, what about when the compound's molecular? The molecular compounds we know about, we can think back to naming to help us. That was like our introduction to these compounds. We know about acids. So we know the strong acids are strong electrolytes. And we know the weak acids are weak electrolytes. So the weak electrolytes partially ionized, the strong electrolytes completely ionized. We know ammonia is a weak electrolyte. So our main prototype for a weak base is NH3. Things that look like it, kind of, but they're hard to spot from your guys' vantage point, so it's really limited to NH3 as our main prototype or prototypical weak base. And then all of our other water-soluble ionic compounds, all of our other molecular compounds that we know to be water-soluble or in solution that we're considering would be considered to be non-electrolytes. So in other words, if you have methanol in water, it's not ionized. We saw that on our very first slide in the chapter 4. So molecular compounds don't have to be ionized to be in the solution like ionic compounds do. So we have examples that are molecular, like alcohols, sugars. If you have anything that's not an acid or base that's dissolved in water, it's going to be in that not ionized into that non-electrolyte category. Okay, now this flowchart here, it's kind of funny. This one from my textbook from a long time ago, 25 plus years ago, and the old edition of the textbook is actually a much better flowchart because I like this as a flowchart a little bit better. It's more or less the same type of chart because it's starting at the top with, is the compound water soluble? And now the tricky part here is that if it's ionic, that's where we can predict water solubility. You know, like, we can't predict water solubility for the moleculars. So let's get into moleculars for a minute. So we're saying, is the compound ionic? And then is it water soluble? If it's water soluble, probably a strong electrolyte. Now, I don't like the word probably that much, but because I'm like really saying it's actually going to be best to call it a strong electrolyte. But practically speaking, if you have an ionic compound that dissolves in water, it dissociates. Okay, so we're going strong electrolyte for those compounds. Now, if it's molecular, the question would be, is it an acid? If it's an acid, the question is, well, is it a strong acid? If it's a strong acid, strong electrolyte. If it's not a strong acid, it's a weak electrolyte, weak acid. So that's why we just have to memorize those 7 strong acids to recognize if it's in that strong electrolyte, strong acid category. If it's not an acid, is it NH3 or a molecular base? And really just NH3. It's hard to recognize the molecular bases. If so, it's a weak electrolyte. If not, probably a non-electrolyte like a sugar or an alcohol. Now, chemistry is complicated. There's lots of examples, like in OChem you'll see, that are hard to classify in terms of acid-base behavior. So we're being really, really general here. We're not really trying to be overly tricky. So memorizing the 7 strong acids so you can recognize the weak acids, knowing ammonia is pretty much our prototypical weak base, and then all other molecular compounds would be into that non-electrolyte category. All right, let's go take our lecture quiz for today. The key word for today is krypton. Element number 36. So we're going to go to the chapter 3 review problems. I think this is the first one in the packet, but it's one of the questions in that packet. We'll do one of these and then try to get back into 1 or 2 more slides from chapter 4 to wrap up for today. But this problem here is talking about aluminum reacting with oxygen to form Al2O3. It says by the given reaction, but then actually doesn't give the reaction. But we can write the reaction very simply because we know, and we should be able to write this reaction without it being given as well. So we know if we have aluminum solid plus O2 gas, that you should get the common ions of Al and O, which are 2 minus and 3 plus. So we should know that you get aluminum 3 plus, O2 minus form as your ionic compound. So then the formula should be Al2O3 to balance out the 6 plus and the 6 minus. So we can predict the products here, and then we can even go through the balancing to Al2O3 to give us an even number of O's, so that's 6. So I can have 3 O2 over here, and then 4 aluminums on the reactant side. So we have 5 moles reacting with an excess of O2, forming 185 grams, and we're asked what the yield of the reaction is. I know probably most of you guys dislike BCA charts, but I'm going to think of one here because I think it's relative. When I have moles in a problem, it lends pretty easily into the BCA chart. Even the excess, I can just think I have an excess here, but I have the minus 4x. I'm going to lose 3 off of my excess. Initially have none of the products, so I'm going to gain 2x. And when I'm thinking here for the minus is reactants are being lost, that's why it's minus. And then the number I'm writing in front of x is just a coefficient in front of the compound or the substance, so minus 4 for 4Al, minus 3 for the 3O2, and then plus the 2 for the 2Al2O3, and of course gaining because it's a product. And so now after the reaction completes, we should be down to 0. So once the reaction goes to completion, we've consumed all of our aluminum. We still have an excess, meaning we have some O2 left over because we're told it was an excess. Then we have 2 times x in the amount of product that's formed. And so then I could solve for x. So X would be equal to -5 divided by -4, so that's -1.25 moles. Not negative, it's negative divided by negative, that's the whole point. It's obviously gonna come out positive. So it's positive, it's 1.25 moles. And so then the quantity of product that forms should be 2 times X. It's 2.5 moles of product should form. What would the mass of 2.5 moles of Al2O3 have? Now, this here is given to us so we don't have to calculate it. That's the molar mass. So whenever you see a compound and either MM equals or M equals, that's the molar mass. Usually you don't see the units, but it could be AMU or grams per mole. So that's just the grams per mole of the product. And so 2.5 moles times 102 grams per mole. So if I multiply 2.5 by 102.0 grams per mole, then I get over 250 grams. So 2.5 times 102.0 would be 255 grams. Now, we can get that from the BCA chart. You could have also then said, well, could I have just done this with dimensional analysis? And you can. You could have just taken this problem right off the bat, skipped the chart. Use for every 4 moles of aluminum that react, we form 2 moles of Al2O3. And then for every 1 mole of Al2O3, that corresponds to 102.0 grams. So obviously the dimensional analysis is quicker, but the thought of the BCA chart helps us get there and understand what's going on, I hope. So I'll probably stop right around this example of doing, both BCA charts and dimensional analysis solutions to most problems. And I get 255 grams here as well. Just making sure that I get the same numbers, same mass as I should. Then my yield would just be the 185.0 we obtained over the 255 grams times 100%. That's probably D, but let's double check. Yep, so that comes out to be answer D. All right, let's think a little bit about acids and bases before we depart here today. So let's take a look at how acids and bases neutralize each other, because they neutralize each other in very much the same way as our metathesis reactions did, except where we don't have the formation of a solid driving these reactions, we actually have the formation of water. So if I take a strong acid and a strong base, so we have HCl is one of our 7 strong acids, KOH is a water-soluble hydroxide salt, hence a strong base. We take these, mix them together, the OH minus H plus, when they bump into each other, they form water, which doesn't back dissociate. That's what drives this reaction to taking place. We don't see this. If you take a clear solution of these 2 salts, mix them together, you're not going to notice and see a solid form, and you're not going to see the water form, but water does form, doesn't back dissociate, so water forms as now a liquid. And we write liquid because it's not dissociating, so it's not an AQ, it's not in solid form. Water is a liquid at room temperature, so we just make water liquid. And then the other pair would be KCl for the counter-ion pair for KCl. If we wanted to think about how this reaction really looks, it's H plus Cl minus. Let me write this, leave myself a little bit of room here. So if I write H plus Cl minus, because HCl is a strong electrolyte, so strong bases, strong acids are strong electrolytes. So K plus hydroxide ion. I'm going to skip writing all the AQ tags, but those would all be AQs. K plus is an AQ, Cl minus is an AQ, and then water is just H2O liquid because it's not a strong electrolyte. So water is a non-electrolyte, so we don't dissociate it into the reaction. So then the net change, if I cancel out the spectator ions or identify the spectator ions that are in the same form, it's the chloride, and then it's the potassium. So my net change, my net reaction would be H plus plus OH minus goes to water. So our net ionic for our strong acid, strong base reaction is just the formation of water from the H plus and the OH minus ions colliding and forming water in solution. Now, how does this differ if we have a weak acid? So the only difference between the first reaction and the second is I have a weak acid, weak electrolyte, still a strong acid, strong electrolyte. My product KF is still a strong electrolyte. KCl is a strong electrolyte above, if we didn't note it, and then water, of course, is still a non-electrolyte. So how do I separate the second reaction into its ionic reactions? Well, I can only dissociate the things that fully dissociate in water. So HF I leave as HF. So I only dissociate the strong electrolytes. I don't dissociate a weak electrolyte into my ionic equation. So I leave intact the non-electrolytes, I leave intact solids, I leave intact weak electrolytes. And then I write the KOH as K plus OH minus, still a strong electrolyte. KF, strong electrolyte, KF plus F minus. I'm skipping the AQ tags for our ions. I could write them all in, just messes up the page. And then water liquid. And so what here turns out to be the case is that I only have one spectator. But that's okay, I can have one spectator. Above I had K plus and Cl minus as my spectators. But here F minus is tied up because it's still attached to the H. So my net ionic equation for this reaction is just HF still intact, AQ, plus OH minus forms H2O, liquid, plus F minus. So that's the only difference, is that I couldn't dissociate the non-strong electrolyte HF in the formula. So the net ionic equation is a little bit more complicated, but the thought is hopefully there. Okay, we'll look at some other examples of triprotic acids and see how we write reactions for those on Monday. Have a great weekend, guys.